Everybody can hear me. Good morning, everyone. It is indeed a privilege for me to be standing here with this really distinguished group of audience and friends that I consider friends. Before I go any further, I'd like to thank especially Dr. Jin Orient and my friend Juan Ramirez. Essentially, I got into a bit of a health trouble earlier this year that I almost died, and then they saved my life. So it tells you that it's very good to really know all these good doctors around. Well, this is the 12 years that I've been speaking on this meeting, and I'm really very honored to be here. I remember my very first talk, I was extremely nervous, since I was talking about a subject that truly dear to my heart, which is sun-climate connections. Today I'm going to attempt to try to tell you another talk on sun-climate connection, which I hope will consider as a progress. It has some intriguing title, and indeed I'm going to cover all the three terms: solar radiation, the Indian summer monsoon, and of course, the story of the dragonfly. Oh, yes, disclaimer. I do have to say that I stand here as myself and nobody else, and all the views that I express are strictly my own and do not reflect those of any institutions. Because as some of you probably know, I've really been vigorously attacked for many other strange reasons. One of them is, of course, this latest stuff from Greenpeace, who want to insist that I have no affiliation with Harvard University, which is probably true, since I never was educated at Harvard. I went there as a postdoc in, I guess, 1991. In fact, I almost didn't want to go there, if not for my advisor. He said, "This is such a great opportunity, so you go." Well, I went. And I stayed there ever since for 20 years. And ever since I was there, I was given a Harvard University ID for 20 years. If they want to take that privilege away, I guess I couldn't do anything much about it, but that's the fact. So, I guess my answer to Greenpeace is that perhaps if I'm not at Harvard University, I simply visited Harvard, Massachusetts, and I thank Harvard, Massachusetts for its existence. And if I can say a bit more, is that I do dedicate this talk to Greenpeace for the hope that they will find some peace in themselves and perhaps to be less green in terms of taking so much money and doing all this political nonsense that they're creating. All right, sun. It's indeed a very amazing object. It is one of those giver and energy of life, I think, especially for planet Earth. And as you know, NASA has given the next 20 years to be the great mission that we want to search for life elsewhere, in addition to what we have on planet Earth. And of course, the blue dot there is trying to show you the relative proportion of the size. Size, of course, doesn't matter as much as actually in terms of energetics. So we're going to really examine in details how does that work. I have to make another statement. I really respect this audience so much that I'm going to put in so many technical and really heavy-duty, scientific graphs. I just felt that I may lose some of you, but I do encourage you to ask me questions later on and perhaps ask for references and things to read. I have to say that 40% of this talk that I give, I have been given to the professional crowd, like the one that I attended in Shanghai and Tongji University last year, which is a group of audience that specialize in global monsoon system. So I truly believe that you could easily understand any of this argument because, it's just some of those things that we ought to be able to better verse ourselves. Like if you truly think that sun could affect the climate system, the whole privilege of being a scientist or even a lay audience that is really curious about things is basically to answer the question, how? Right? So we'll try our best to try to do that, and I hope as a role of a speaker, I can try to inform you of some of these difficult journeys for 20 years that I've been trying to study this object. Let me start by explaining the climate system and how the sun play a role and how the CO2 could supposedly play a role. Just imagine that the climate system is this football player, Refrigerator Perry. Okay? And then just imagine what the sun can be and what the CO2 should be. For the sun, I would say it's the King Kong of the climate system. And then CO2, as we know, probably we best give it to Vice President Al Gore since he loves CO2 so much. But then let's hear the argument. The standard argument from IPCC is really can be trivialized in these cartoon analogies, but I think it's fairly accurate. Okay? The whole argument about why the sun is not important, whereas the CO2 will be extremely important, in the sense that it will govern the next climate change, not only the past 20 or 50 years, it will guide the whole climate change for the next 50, 100 years if we don't do something about it. That is the magical forcing that we're dealing with. But the argument that they put out is indeed this way. They say that, well, the reason why the sun could not be important is because the sun was on diet. He's been taking some water. Switch the picture from King Kong to basically a gorilla because it's really difficult to find King Kong, gorilla, gorilla or King Kong. King Kong that actually drink water, so I have a gorilla picture instead. Then the argument that why CO2 is important is indeed that they say because the CO2 has been taking a lot of hamburgers. Mr. Gore has been eating a lot of hamburgers and he's been gaining weight. So this is why that they argue that Mr. Gore could easily push, because of the hamburger that he has taken, could easily push refrigerator Perry up and down, whereas the sun would not be able to do this. Okay? All right. Then, let's see. Well, you know, indeed, I would argue, and I'll show you the quantitative details in a minute, that I would propose that even if Al Gore have another... Oops, excuse me, I got a phone call. Let's see who this is. Hello? Oh, Mr. Gore. Oh, you like to order more hamburger? All right, how many? 20? All right, that's fine. I'll send it to your room. Thanks. Well, I really don't believe that the hamburger will be able to allow him to push the climate system so easily, whereas the sun will truly be the driver of the climate system. Here's a bit of a joke, and people say I shouldn't put up this picture, but I'm politically incorrect in a lot of sense. Well, here's now how IPCC framed the whole problem. They say that imagine this climate system that will behave something like this. And then they created such a wordings and parameters. They call this net radiative perturbation to the climate system. And you will hear a whole lot more about the insights on how climate system and the weather climate system should behave from Professor Christopher Essex later on. But here they argue that because if you think in terms of this parameter called the net radiative forcing, then over the last 150 years, the CO2 would be able to push the system by that number, 1.7 watt per meter square. Whereas the sun is only this tiny little bit of 0.2. That's essentially the argument of the 20 hamburgers versus the water, right? Okay? And then I just want to tell you, of course, I took those numbers from IPCC. I'm not going to challenge the sun part for today because you do not even need that argument. The sun number could probably be easily 1, okay, for this particular purpose. But let's now look at the correct way of thinking about the climate system. I really propose that the correct way to look at the climate system, and by the way, the two figures just provide the similar information, essentially. Now I say if you think about the climate system as something truly from the sun, which includes something called the weather system, the season and the climate itself, because if you think about the previous graph, you essentially thinking about a climate system that do not have weather, do not have season, do not even have mean climate, by the way, don't have any climatology. It's just simply that you think of it in terms of net climate change, all right? So I think this is the better proposition to try to think about how the climate system and weather should behave, right? Because 341 and 341.2 is essentially that 0.2. 33.7 and 32 is that 1.7 difference. But if you look at it on the sort of what I call the absolute scale, then you will see that CO2 perhaps would not be such a powerful player after all. And I'll go into a bit of the detail to try to explain this reasoning. Oh boy, here now comes the IPCC to help you to learn a bit about weather and climate system. As we know, the Earth's history has essentially undergone quite a lot of this ice ages history, up and down, you know, middle warm period, little ice age, so on and so forth. But in terms of IPCC, they indeed try to always downplay the role of the sun. Here's one of the tricks that they have been doing. And this thing really bothers me a lot because this is a standard climatology that's been known for at least 40 to, at least I would say 50 to 80 years, ever since Milutin Milankovic, that Serbian engineer who came up with the idea of orbital forcing on climate change. But the way they downplay this is that I'll explain in a minute, is that they say, okay, the sun effect, which is from this orbital changes, which is perturbation of other planets of the position of our planets, either from the tilt position, right? And then the precession of the orbit itself. And then, of course, the changing of the ellipticity, how circular or how elliptic is the Earth orbit around the sun. That these three factors will contribute so little if you look at this idea of radiative perturbation to the climate system. Whereas Mr. CO2, and now they could even add those gases, those cow gases and so on and so forth, the laughing gases, to be so important. In fact, worthy of a laugh here. That's why I'm saying this is where the problem with IPCC begins. They always manipulate information, and it's a shame actually, and it has to be stopped. And somehow nobody wants to stop them, and nobody even wants to say that this is a stupid graph. Don't ever do that. Here's the explanation. They try to tell you to think about the climate system as this global this and global that, right? If you think about the Earth history, this is purely from the geometrical changes of the sunlight projecting on Earth system, just due to the orbital effects, right? The changing orbital configuration of the Earth relative to the sun, is that over the last 1 million years, okay, going from left to the right, present is 0, where the net global annual mean radiative forcing on the system is only 0.6 unit. Whereas if you think in terms of how radiation is being received on planet Earth, therefore you can begin to talk about weather and climate system, is that you would rather think about it, and that's the idea proposed by Milutin Milankovic, that servant engineer that produced this idea, would be that if you think about it as a high latitude location, like here, peak 65 degree north, okay, the energy input of the sun coming through that particular high latitude region. Because as you know, ice grow in the high latitude region, right? I mean, it's essentially then Milutin Milankovic is saying that it is indeed the summer sunlight, incoming sunlight, that is very, very important, okay? If you have actually stronger summer sunlight, then you will melt more of the ice that you accumulated over winter, so therefore you have less ice accumulation. If you have weaker incoming sunlight during the summer, then your ice could accumulate more and more and more to the point where you build ice ages. You have ice ages that is 2 miles thick in New York City and Boston and places like that, okay? That's a very significant forces, where the total net energy change is only 0.6. But at an individual location, you can see the units here is about 100 watt per meter square. There is no way that the CO2 could do any such thing, okay? It is purely from that effects, and there's no need to account for anything else. CO2 is merely a passive gas that is being pushed around by these effects from such changes that will be very, very important. This is another way to look at this. Just think about the seasonal cycle amplitude, sunlight. Present, which is the solid line today, and then during the so-called Eemian time, the last interglacial, roughly about peak at about 16,000 years ago, where the amplitude of the seasonal incoming sunlight could be as large as another like 90 today versus 3 times bigger at about 230 watts per meter square. So for those who say that the incoming sunlight is not important, that is just a laughable proposition. And in fact, I try to propose that it is all about season. In fact, I'd say that large part of the meteorological problem and climate problem is actually related to how well we understand seasonal climate change, okay? Because no 2 summers are the same and no winter are the same. This is just essentially my one long sentences of trying to explain what climate is. I try to tell you that it's first and foremost is the systematic persistent in weather pattern and fluctuation involving the seasonal and annual cycle, not just the mere time average weather statistics. Like these people try to say, World Meteorological Organization try to say, well, climate is just a 30-year average of the weather. Excuse me, 30 years? Why not 50? Why not 100? Why not 1,000? Okay? It is just a convenient that you can perhaps use it to teach classes, but it is not the truth. That's the whole point. So you can read all about this, but it's showing you the complication in terms of how this weather and climate system truly operates in this sense. And that's the framework in which I formulate my sun-climate connection. I was indeed on the wrong path for a long time, maybe the first 5 years of my research, but I was slightly quick, but in 15 years, it still take me 15 years to figure out this, okay? So I like to say that it is simply internally inconsistent. For science, of course, once you have such a damaging internal inconsistency, you are finished, essentially. You know, all your ideas is just crazy, actually. So, you know, it's not going to be the reality. So I'm saying that if you accept the role of sun for seasonal cycles, which IPCC agree, which Fred like to frame it that IPCC, but it doesn't matter whether IPCC agree or not, it's the truth, okay? So if you're simplistic rejecting this contribution for changes on another timescale, then it's very wrong. Oh, that's another very, I guess I always been, when I talk about this kind of thing at American Geophysical Union, for example, they say, wow, the climate model, come on, they know how to do, they can tell you that summer is going to be warmer than winter. Oh, thank you very much. What a smart climate models. And then there are actually even more profound statement from actually Professor Robert Kerr of Rice University, who indeed wrote such a statement that, you know what? All this basis of IPCC is so secure and so carefully researched that it's not just based on one particular models, it's based on so many of these different models that give very similar result. Therefore, we have some confidence, And then people say, why don't you just put all these seasonal effects and put it in the climate model? There comes the output that you're going to be giving you the answer. I say, not so. Let's check some facts. Here's the fact. If you look at all these 24 climate models, okay, the output from these 24 climate models, and here we are only examining that simple issue that I'm obsessed with right now, just the seasonal cycle. If you just study all the available station data for just on the land, where you study just the amplitude of this thing and the relative phasing of certain season arriving, so plotted at the bottom there, and then the amplitude is on this vertical axis, and then you ask yourself, the trend of these things, where does the model fall? They fall all over the place, okay? And then let's ask where the real world observation is. It's right there. And I would say if those who want to keep insisting that the GCM can do all of this, which is the climate model, the general circulation model, that they can do it well, it's just not true, okay? And then, of course, there are even those who try to say that, and Professor Christopher Essex will elaborate more about this problem. You say that you can just take, why don't we just take an average of these things and then we'll find some good answer. It's as if that you average all the floor model, you will get a better result somehow, which is a very strange proposition. So in this sense, I like to propose that this analogy works very well for explaining why you shouldn't do that. Just imagine if you have all these different jets, passenger jets, and then you ask yourself, what would the average look like? Indeed, we do have an answer. It's very fuzzy. And probably not the right answer, put it that way. I wouldn't go on that kind of fuzzy jet, by the way. So the bottom line here about climate model, my true criticism is that indeed, give me a faster computer, I'll give you the wrong result sooner. Joking aside, but there is some essence here. I would say that the more worrisome aspect of the climate model is indeed this. If you happen to see observation and climate output disagree, you should be very grateful. It's okay. You will be very worried if you see that climate model and real-world observation data agrees, actually. Because you can almost be sure that the agreement comes from the wrong reason. That's exactly how flawed this climate model approach is in that sense, which is really, really one of the fundamental problems that I'm unable to accept this reality that EPA, IPCC, what have you, is trying to impose on us. Here's the reason. Here's one example to try to show you GCM on your left, and then CALIOP, which is the observation new data sets, on the right. And looking just in terms of cloud fraction distribution from northern hemisphere to the southern hemisphere, minus sign on your left to the right, northern hemisphere, and then looking vertical scale up. Okay, this one is in the tropical region. No, the whole region, the whole world. But you look at what GCM output versus the real world data. It's truly not very good at all, actually. This is part of the reason, because cloud is one of those nasty variables that is extremely difficult to model. Okay, so I would not have too much confidence for this kind of thing. That's the reason why if you get an agreement, it's almost sure that you got it for the wrong reason, because they simply don't get cloud and water vapors and all those distribution correctly. Here's another example. On your left there are two data sets now of labeled observation. They don't quite agree with themselves too much, but at the lower layer, let's say about 800 on that unit, which is maybe, I would say, only 2, 3, 4 kilometers up, that they have this very, very serious high value of the cloud water. This is actually cloud water content, CWC, okay, measuring that variables. Right? It kind of have very high measurements, and then you can see where the model stands here. It obviously didn't produce anything close to what reality is saying. So this is why, fundamentally, one should never ever trust climate model of this kind, of this kind of quality. It's just simply not up to the task. Okay? Oh, then I have a short intermission before I get to my Indian monsoon. It is often claimed by skeptics that IPCC model has failed to include these effects of cosmic ray on cloud. And I just want to ask the question, is it true? Because some of us who still believe that perhaps it is the incoming galactic cosmic ray, that's the idea, right? That essentially modulated by what the sun is doing, then depending on how strong or how weak the sun is, then the incoming cosmic ray that come down to the Earth's atmosphere, especially even towards the surface, would be a very significant source for ionizing the air. Essentially, the idea there is that then you have this free electron running around that will get attached to some of these particles, aerosol particles. More or less, they produce particles in a nanometer size. Nanometer, as you know, is 10 to the minus 9 meter, right? Very small particles. That then this attachment of this electron to that will have this thing called the enhanced nucleation process. Then you essentially will be able to form up more particles and then glue more water. Essentially, you'll make clouds. That's the idea. My bottom line of this is that this idea is very beautiful. As soon as it came out in 96 and 97, I was endorsing the idea. I believe in it because I look at the data, it's simply convincing. But by 1999, actually my first talk, 2000 here, I already disagree with that viewpoint. I already discussed with the inventor of this idea, which is Henrik Swymark of the Space Danish Institute. They just simply doesn't work because I believe that this thing would only work for a small little patch of sky because cloud doesn't work by microphysics alone. Especially the low cloud that he claimed there's an observation between galactic cosmic ray and the low cloud cover. It's essentially a place where you don't have any shortage of particles around to form these things. That's just not a question of that. It's just simply a problem of formation of cloud by large-scale phenomena like inversion layers, things like that. Collision of cold and warm air and things so on and so forth. But the idea here about skeptics saying the IPCC model didn't include all of this is just not true. In fact, they have done it. Here's a scheme that came out with the most prestigious group, the Max Planck Institute for Meteorology. They try to work on the aerosols, which is the H2SO4 things, nucleation, and then try to put that into the climate model. They simply say this problem is so easy, we'll just put it in the climate model. It can be done, according to some famous geographer. Then they will say, okay, let's look at the output. Just put these processes into the model. That's easy. Then we just study during solar maximum, where you have low galactic cosmic ray, GCR ionization, and then during solar minimum, you have high GCR ionization. So let's look at what the output is. Here's the bottom line. Well, the global average, again, is minus 0.028, extremely small. So therefore, they conclude that this cosmic ray effect is flawed, right? That I don't think is a good way to test this, by the way. So I simply want to give you an example that it is simply not true. Those guys have already studied that, the issue that in climate model. But this is another very strong misuse of climate model that I want to point out. Now let's get me to reality, the subject of my interest. I started with this old graph. So what is my thinking on sun-climate connection? How does it work? I really, like I told you, I think that you do not need to understand anything except for just the incoming seasonal sunlight, okay? Because of the geometry of us going around, changes ever so slightly, plus that the sun intrinsically could change by itself from the changing magnetism on the sun itself. Then you modulate the output of the sun, right? But here is one example. You can estimate how much the sun solar output has changed in terms of the light output, not the cosmic ray stuff. It's plotted by the red line. Some of you have seen this many times, but don't be bored with this. This is really a very valuable empirical evidence. Then I plotted the dotted blue curve, which is this Arctic surface air temperature. Clearly, it looks very interesting because it has some sort of a resemblance when the sunlight increases from 1900 to about 1920s and 1940s. You can see that the Arctic temperature appears to warm up. And then from the peak warmth from the 40s, when the sunlight actually started to dim ever slightly from 40s to about 60 or 70, you will see the system somehow cool somewhat, or even not increasing warmth. Then finally, the last phase of it, when the sunlight appears to be slightly increasing, that the Arctic temperature warms up again. So you have that kind of empirical evidence to try to suggest that the sunlight does indeed modulate what the Arctic surface temperature could do. Here's a more detailed comparison of the Arctic temperature, because have to remember, the whole climate system should not working on global this and global that. It's all on regional scale that is very important, the local and regional scale, which I'll get to in terms of monsoon system. Here I'm showing you the results for Arctic wide surface temperature versus the solar output, and then Atlantic sector, the Pacific sector of the Arctic region, which is from, of course, 66 or 60 degree north to 90 degree north, Greenland and Icelandic sector. It shows you that there are some coherence in terms of the empirical evidence available to suggest that there's this influence. Even on a scale down to the local station scale, where here now I show two instrumental data sets from Gotthard Noob on the southwest of Greenland, and then Amasilik on the southeast of Greenland, where you can also see some resemblance of the changes in the solar light output versus the temperature changes there. So what this is telling you that there are some consistency in this hypothesis. Okay? So now let me give you the details of how does this all work and be put together. But the question is indeed, why and how? What I'm trying to suggest to you that despite all these details, it really can be simplified by a statement like this. What I suggest is that essentially this incoming sunlight changes ever so slightly from the changes of the sun intrinsically, and then projected through our motion around the sun over year by year. Then you provide this, what I call the persistent forcings and modulator to the dynamics exchange of the heat flux between the equator and the Arctic. Okay? And I'll show you evidence for that. And then essentially what you do there is that you modulate what is happening on the Arctic. There, I want to speak in terms of the modulation, not only the temperature sense, not only the heat sense, you are modulating actually the freshwater budget. You are also dealing with the cryosphere. If you have more heat there, you will actually melt more snow and ice. So you provide actually a freshwater differences that eventually will get expulsed and come out through Greenland area, whereas essentially you will then tap into this famous thing that is happening, deep oceanic circulation in the North Atlantic, where it's called the thermohaline circulation or meridional overturning circulation. Essentially, then those effects will propagate from equator to pole, then it propagate very quickly all the way from north to south further. I'll show you all of that evidence in a minute. That's the detail of how you can formulate a hypothesis that you can reject if you can show evidence that is wrong with respect to this scenario. So this is the way to think about this system. Here, actually, the map here is plotting salinity. It shows you indeed that water is very fresh in the Pacific, but very, very salty in the Atlantic. And what I'm trying to show you is indeed the path. This is the oceanic path is shown by those dark arrows, which is going through the Bering Strait. You see this is water flux going there. And then it's very, very less salty in the Arctic region, the Arctic basin. And then essentially those water get expulsed, okay? So if you can modulate what the freshwater budget into the Arctic is, then you essentially will have an ability to tap into how the North Atlantic salt and freshwater budget will be. That's my idea of this sun-climate connection, which I hope that Professor Bill Gray will also illuminate more about his idea about how this whole thing could work, which he clearly disagreed with me. That's part of the nature of being a good scientist. And then essentially then the effects will come in through this weather vane signal through atmosphere, which is another fast process coming from Atlantic to the El Nino region. Okay? And then the other side is actually from this monsoon region that is also very important. Now, the first evidence. This result actually is fairly new. I haven't published it yet, but it's a work based on two of my colleagues, David Legates from University of Delaware, and then Kaushik Dutta, which I'll introduce in a minute. He's a very, very good young scientist from India originally, but now he works at University of Minnesota. And here I'm trying to show you that if you take the same solar output data, which is the red curve, and then if you study in terms of how the equator to pole temperature gradient changes for DJZ, JF, which is December, January, and February, which is all the 4 seasons, and then the spring, which is March, April, and May, and then summer is less clear at all, so it's not good. So on 4, you have a similar also pattern. That gives you a lot of insight into how the heat budget and energy budget are being redistributed from equator to pole. Okay? This is actually a very long search that I believe that most dynamicists of the climate system want to know this. Is it true or not? And we now have the first empirical evidence that I can show that indeed such a thing may be true. Okay? I'll talk a lot more detail during my publication, of course, on these effects. Then what happened there? Once those heat are alive in the Arctic, do we have evidence then you actually melt the ice in the Arctic itself so that you can create these freshwater and salt imbalances. The short story is that if you look carefully in terms of the temperature curve, which is the black curve here, okay, and then you look at the most latest result, what we call the Zakharov ice data from Russia, St. Petersburg, which is the red curve, you will see that during the 20s and the 40s, when the Arctic temperature is warm, indeed you have ice slightly lower and then come back again in that. There's another data sets that don't agree with this idea, but the whole purpose in science is indeed you show data that agree and disagree both. You don't hide any evidence. The whole idea then to ask which data set are slightly better. Do we have additional evidence to try to suggest that such an effect that I'm suggesting, that especially during the 20s and the 40s when you have enhanced gradient of transport of heat from equator to pole, do you melt the ice? We don't have much evidence on that sense, but we can show. First, from the satellite data, during the warm period of 79 to 97, you indeed have region of minus. You see the red place here is minus percentage in terms of changing in the ice coverage area. There is a huge amount of ice loss, okay, during that warm period. But here now, for 1916 to 1995, there is a way in which you can get that information. This is another good way of using climate model, by the way. This is called a deduced information from a very, very sophisticated model that's studying the Arctic. That will show you that indeed, for this period, you do have very large, significant loss of ice area in the Arctic, which will explain some of this support, partially the ideas that I'm trying to suggest here. Okay, so you can remember looking at that bottom part, that we have that kind of information. So that's the whole cartoon picture of showing you the complexity of the oceanic circulation. Okay, either depends on the depth. There were all sorts of these arrows and circles and things showing around, showing you the transfer of energy and heat and salt and imbalances. That what we bottom line want to tell you is that this whole freshwater flux could come out from here, Davis Strait, and then through Denmark Strait right here, where then you will tap into the sinking region of the North Atlantic, where you can actually tap into the overturning circulation. And why do we say that it has to involve this thing called deep overturning circulation? Remember, this is a winter phenomenon of a convection phenomenon that is started to get cold. The water can reach from the surface all the way down to 2,000 to 3,000 meters in the North Atlantic. And the proof actually comes from these two data sets, the paleo data, that was very much around Labrador Sea areas, two of the data sets, but they are at different height. One of them is plotted here. The red curve here, 1,000 meters or so at the bottom depth. Another one that is deeper one, about 1,800 meters. They are showing two different signatures, obviously. But the point is that you see here, if you put that curve of the 1,000 meters, you look in terms of how it get connected to tropical Atlantic, which is measured by these particular variables, you see there will be no resemblance. But the one at the bottom, that during the place where you overturn, you actually have some close resemblance. This is why you really need this overturning circulation, which is the flywheel in the climate system that distributes energy around. And in my simple sense, I was able to show you that, by the way, it does take another really important signature is that this effect comes all the way from North Atlantic or the Arctic and propagate down southward. It does take time for that to happen. And I estimated that that thing would take about 10 years. So if I do that delay and then I make a plot of the overturning circulation measurement that is available, that you will see that there are some resemblance, especially the red curve versus the blue dotted curve that you show here. Again, I have a picture in which I can show you the empirical evidence of how that relationship should work with the delay. That's a key mark of this hypothesis. Okay? If you plot straight, you will not get the answer. Then showing you amazing phenomenon. That's why you have to involve this overturning circulation in the North Atlantic. Here we are connecting Nordic Sea area, very far to the east, North Atlantic, and that which is plotted by the blue line, and then Carical Basin, which is Venezuela, all the way. If they don't involve this overturning circulation, I don't know how would you have this very interesting close correlation between the two variables. This thing is all the way south, okay? Tropical Atlantic, South Atlantic essentially. That you have that kind of connection. And again, shows evidence for the last 1,500 years. You have evidence for medieval warm period 2 versus the Little Ice Age. And then even more complicated in the sense that trying to show you that essentially the variables that you have available in northern Gulf of Mexico that can tell you something about this, what we call the intertropical convergence zone, ITCZ. That variable I'm going to use a lot, especially when it comes to Indian monsoon. This is essentially the rain belt that follow the angle of the sun, going from south to north. So when you reach like peak of the warm in August, they will reach the northernmost position, and then they move south again when your season goes away. This rain belt is very, very important. Okay, going north-south depends on where the sun angle is. Okay, essentially what they do is they provide the intergradient between the hemisphere, basically in the tropics, that provide this kind of movement north-south, but it's very important. Here we show a very interesting correlation over 1,000 years or so between estimate of the proxy of the solar activity versus this movement of the ITCZ north-south. This is very, very important evidence too, in terms of showing you that the connection not only extends for the last 150 years, it extends over 1,000 years at least. I think by now most of you get the headache, so maybe I should not attempt to explain this thing, but that's the whole idea. The whole idea is that there's a way in which you can view this and try to understand about the fresh water budget and salt budget, that you can have this somewhat cyclical, okay, oscillation in the system that is essentially caused by the persistent changes of the incoming sunlight, that ever so slightly modulating the direction of where the heat budget will go one way or another. Okay? And then, now we come to the Indian monsoon region. What I told you is all in the North Atlantic. How does the effect get propagated down towards actually the east? Like down to India, down to China. Okay? That's actually all my new work here. Today I'll show you something about the Indian monsoon region. I have now a new work that I just done on China. That will be fairly exciting. I talked a little bit about that 2 weeks ago at the Heartland Institute meeting in DC. But now today we'll talk about the Indian monsoon region. Essentially what the effects I'm trying to tell you is that it will somewhat involve this something called the phenomenon of the jet stream. Okay? This is air that is circulating in 10 kilometers or 8 kilometers up there that is running about 100 miles an hour really quick. But essentially that effect could propagate through that effect, through this circulation. But what I want to mainly show you is that, you know, this topography of the region, in here I'm plotting you how those North Atlantic phenomenon, which is shown by AMO index, could actually modulate how much the troposphere heating actually at this high altitude region in Tibet, in all those regions in Himalayas. What you can show that there is that kind of a modulation. Once you can prove that, then those regions in the northern Himalayas essentially will show you a very, very important controlling factors for how the budget would happen in terms of the Indian monsoon region. I'll show that in a minute. Once you tap that, because how warm or how cold you are in terms of the land region will show you how strong and how weak the Indian monsoon would be. Okay? This is the evidence for the temperature, which show you that the effects mostly show up in the Chinese region, the China and East Asia region, rather than in terms of temperature, rather than India. But in terms of precipitation, which is one of the key variables, rainfall, you show that most of the effects show up in especially JJA, Indian summer monsoon. Look, that shows you that when the AMO is strong, okay, which is the sun energy being strong, the input is strong, then you have a lot of more rainfall, which is weather, the blue region here. So this is the place where we're going to try to show you that there's such a connection. Okay? And here's one way to show this, which is to plot the AMO index versus this index called the All-Indian Rainfall data sets. You smooth the data because you're looking for something that changes on multi-decadal changes. Every 20 to 50 to 100 years kind of changes. The data length is very short, but I'll show you some of the data can extend another few hundred years or so also later. So this is the motivation, by the way, for the problem of how you show this interconnection. So what I illustrate for you is that indeed we have a plausible scheme that link how the changes in the solar total irradiance forcing modulating the equator to pole temperature gradient, and then ultimately the Arctic surface air temperature, SAT, and then the Arctic freshwater flux, and then eventually you will get into tapping into the energetics on the Atlantic thermohaline circulation, and the ITCZ, the Intertropical Convergence Zone, and then the related interconnection to ISM, which is Indian summer monsoon, and then East Asia summer monsoon, on multi-decadal timescale or longer. It's a mouthful, but please, that's the details that we have to know to be able to say that we know something about how the sun could affect the system. So I mainly want to now promote two of my young friends. On the left there is Rajesh Anindori. He's from the National Physical Laboratory in New Delhi. And then Kaushik Dutta, which is from the Large Lakes Observatory at University of Minnesota. This is now going to be a work that we just published. We just got accepted the paper. And if anybody interested, of course, please let me know. We'll be happy to send you those papers. Obviously, I think you will be the first 100 people to see this ever. So now let's start with the Indian monsoon. How does it work? Well, essentially, as you can see here, a plot is basically the surface wind picture plus the surface sea level pressure. Okay? High region is all towards the south, and this is for a summer season. And then you can see the land got all heated up, so they become a low region. So you have a lot of this convection. When you warm the land, it started to bring air up to the air, and then you started to draw in air from the ocean, where you can kind of see this key region of the what they call the southwest Indian summer monsoon. You see this turning circulation, the arrows is showing the surface wind is moving in from the ocean, right? So from southern Indian Ocean towards the land. That's why you also bring the moisture, bring the rain along, okay, that you get this modulation of the Indian summer monsoon. And here now, the first start, which is to look in terms of the total solar irradiance index versus those all-Indian rainfall data. It really doesn't look very convincing, actually. Okay? So we didn't see no evidence on that. So what am I trying to pull here? Well, I'm trying to suggest to you that in terms of looking at this picture, one has to think much harder about this. The somewhat, quote-unquote, magic come from the idea of Rajesh Agitori and Kaushik data. I was just merely helping them along. So this is not my idea at all. The credit should go to them. Is that they think, why don't we think in terms of because we talk about how system should change its response to changes in differences, a gradient, energy output input from Indian Ocean to the land. So why don't we compute this variable called the insolation gradient, or compute some kind of derivative with respect to that curve? And when you do that, which is the bottom curve, plotted as the red curve here, and then you plotted two of this Indian rainfall series, you're beginning now to see that depending on whether the derivative of the TSI index, whether it's positive or negative, that you will see there was some correspondence. What here I'm trying to talk about the situation is more towards the more important one, which you have negative derivative, where that's the part where you have less rainfall, you have drought condition, and then you know that in India, those are fairly significant situation in terms of societal response to those drought condition, which is famine condition. Okay? That I don't want to go in detail, so we can extend this data set instead of from instrumental measurements. We can go back using a cave stalagmite data and go back about 300 years. And the top curve is the same thing. The red curve is showing you the derivative of the index. And then you can see the major drought that is very well known in 1876, right there, right at the bottom there. Right? And then it corresponds with the cave information plus the negative TSI index really agree with it. And then ultimately, you can see right here, if we look at multiple evidence in terms of record from instrumental data, from tree rings, from cave data, you will see that they all converge in terms of when you have this drought condition, you may have famine, but it's also correspond to the negative TSI derivative that we derive in this new index. I think this index actually help you to learn a little bit more about how the system should behave. And I think this is very exciting in terms of trying to understand the Indian monsoon, which no one has ever thought about in this way. This is why we published this. And here's the consequence, that famous 1876. See that thing right there? Here's the real condition. It's just amazing that even put them on the chair and take a photo of this. Just disgusting. But anyway, that's the reality of when you have such a condition, a drought condition. Then the societal influence, if we're not prepared for it, is a very severe consequence. Then I want to talk about another fact that is very well known in this Indian rainfall data. Actually, if you smooth all this noise of a weather data out, you will see that you roughly have a 60-year cycle, which is very interesting. What it points to is that indeed there are some kind of oscillation. There's semi-multi-decadal that is quite regular. Come and go, come and go, come and go. What this kind of gives you a hint is that if you look at the data on even longer time scale, here from the earlier work from two of my younger colleagues, Rajesh and Kaushik, they study this data actually from about 1,000 years. They got this from a sediment core in Northeast Arabian Sea of the Gujarat coast, where they were able to show that indeed such a phenomenon of 60 years oscillation exists in these measurements that they were able to do, the organic carbon content and the nitrogen content in this sea sediment that they were able to drill and get out the data. And then you can see that the sun, in terms of that, there are some hint a bit of these multi-decadal changes, okay? That shows you that perhaps we should think a little bit more about this instead of dismissing the information outright that say there's no connection of suns with the Indian monsoon. So I guess the only question left is that how to prepare for this cycle of droughts and famine. For that, I guess I'll just motivate to the last part of my talk, the lessons of importance of water, lessons from the dragonfly. It turns out that this is a fairly amazing story. And I call it, actually copy the local people from the Maldives Islands, called the He Nakie Duni, which is the October flyer story. It's about a journey of this particular type of species of dragonfly who's actually apparently able to cross large portion of the ocean, reach the land in Africa, and then return back. And this is actually an original finding by this person by the name of Charles Anderson that lived in Mali of Maldives. It's based on one of his talks that is worth everyone looking at it. It's really a very interesting story. So this is that particular species. It's called the global skimmer, and it has very large wingspan at the bottom, and these are really tiny little insects. Okay? The question is that what happened to them? What's going on here? What do they do? And here is now talking about how the dragonfly actually supposedly, apparently arrived from Indian continent, South Indian continent, and this is the date where they started to arrive, reaching Mali on average about 21st of October. And then in different locations, as you can see. Mali, actually Maldives Islands is very large, covering like maybe 0 degree to 7 north or something. So it's a very large region, but reaching Mali right about October. And then there is evidence that those butterflies actually come further north. They're migrating during September towards the south. Okay? And then they're even coming from Ceylon, Sri Lanka, towards this way, towards the Indian, and perhaps go to Maldives Island. Look at the date. It's September and October. What happened here? This is still in the main phase, the end phase of the summer monsoon, where the surface wind is actually moving southwest, from southwest. How do this dragonfly, who's supposed to come from Indian Ocean, facing a headwind and would be able to reach Mali that way? That's the puzzle. And also, why do they want to go to Mali, Maldives Island for vacation? I don't think so. Now let's explain, right? Apparently, they are taking this long journey. Okay, and I'll explain finally why in the last few view graphs. What they are able to do is essentially come from southern India, taking that long journey, arrive in Maldives about October, and then there are evidence that they arrive in Seychelles by November, and then Adabra, December, and then essentially they've even been found in Kenya and all the way to South Africa too, this southern region. So they're taking a very long journey from that way and then come around and then turn back also. We even have evidence that they actually went back later. And what are they doing this? And that journey, if you cover it properly, it's actually about 14 to 18,000 kilometers. It's so probably, if proven to be true, will be the longest journey by any of this insect ever done, because the longest one ever known is the march of the monarch butterfly, right? From southern Canada all the way to Mexico. That's only 7,000 kilometers. But butterfly doesn't go back. These guys apparently go there and go back again. But of course, it takes several generations. It's about 4 or 5 generations of this butterfly who born and live in motion. The answer is that they essentially are looking for fresh water to try to follow the monsoon rain, the path of this monsoon, to try to look for this for survival, basically. Okay? That's the bottom line. Hey, it's not only the dragonflies are doing it, even the birds. Some of this example, the falcon, the hobby, the paichuku. The paichuku is the only one that is known to actually go from India, perhaps even reach Africa, and then they go back too. The rest of it, we don't have evidence for it, okay, that they even return it. And here's one, and then you guess why? Why they're doing that, right? Because they kind of go along together, and then eat these things, and then survive all along. And then now, let's hear the story of dragonfly. Why are they doing this and how they do it? They are essentially, well, let me explain a list first, because this monsoon system is very interesting. Here we're showing the land-sea temperature contrast. Yes, you can see the warm region are very red, bright red region, and then the green region are actually the cool region. That is actually, for the top there is basically the winter monsoon, for Indian monsoon. Then the wind is actually blowing northeast, okay, from the land to the ocean. For the summer, you will see that you are essentially warm out the land a whole lot more, then the wind is drawn in this way because you have all this uplifting air and then the wind got drawn in from the ocean. That's one way to think about this. And then you also have to look at, well, that's fine. That's showing you the monsoon. Then you look at the surface wind, which is again showing for you that for winter, it's actually going northeast in the surface. And then for Indian summer monsoon, you're going southwest. Okay? It's showing you again this seasonal movement of these things that is very, very important. Then the most important one, which is the rain belt. Okay? This is a satellite image that kind of show you the average position of what they call the ITCZ, the Intertropical Convergence Zone that I told you is very important. We kind of want to focus on that. You see that during summer, during the August, the peak month, all the clouds are forming over the continental region, right, where the rain belts are sitting there. Okay? And then they move south as you come towards the summer of the southern hemisphere. They don't go too much south, by the way. They just reach around the equator region, the rain belt. So these rain belts are very, very important. So the bottom line is that apparently all these animals are following the rain belt, essentially. And how do they do it during October? Because the first arrival of the dragonfly at Maldives, is October. October, as you can see, the surface wind is still southwest. Apparently what they are doing is that they are actually following the ITCZ movement, the rain belt, which is started to move south. Okay? And then essentially it coming at an inclined position towards the equator. So the top here is inclining, imagine the equator here. The bottom there air is southwest, but the top air is moving northeast. Right at about the height about 1,000 to 2,500 meters. So they are coasting along in this upper part of it. And we know that those guys are capable of handling this kind of height. We know that the species of dragonfly that they found there, this global skimmer, actually also go as high as Himalaya. In fact, they won't freeze to death or die or something because even at that height, it would be cold enough for those animals to survive. So they're coasting along, they come here. Okay? So they apparently are able to do that. And then when the rain belt started to arrive by November, you can see it's the peak population in the dragonfly in Maldives. But what are they doing to Maldives? Maldives, as you know, is the coral terraces that build up all these chains of islands, right? That basically there's no fresh surface water. Why are they doing that? They're actually following the rain belt to survive from actually, they know, by the way, they even do it a month ahead. Because the winter monsoon started in India, it's around November or December. They started moving from India in September and October, they know, a month ahead to come. Because they know essentially you're not going to have much water already on the land in India. They started moving south to follow the rain belt. And the fresh water there is very important. They're actually looking for this, what we call the ephemeral water. That water there is just born there. They essentially don't have the predator species like fish around to eat them, the larvae. But you can also make a lot of mosquito things that where they can eat also along. It's just amazing made of nature that this system, they're able to follow the rain belt. For the Western India part, is basically the monsoon rainfall, right, that they're following. For East Central Africa and Southeastern Africa, they're following the rain belt. The rain belt, the ITCZ, is very complex, by the way. So the peak of those months are all essentially related to peak rainfall, are all related to the ITCZ position around that area. So with that, I guess I would just close my talk and tell you that indeed there are some interesting progress are being done in terms of the study of the sun-climate connection. If I have a chance to talk about it next year, I truly will explain to you an amazing phenomenon that's happening with this jet stream that is going at the air about 8 to 10 kilometers, and will show you how those regions from Indian monsoon to the East Asian monsoon are all interconnected with respect to the original places of the modulation from Arctic and North Atlantic. They are all interconnected, and they are really behaving in that way, and I formulate to the point where you can actually reject those hypotheses, and that's the job that we must do. Thank you. Do we have time for questions?
We have about 5 minutes for questions.
Very good.
Okay, I'm going to ask a question. You made a statement that the radiative forcing from the sun on an annual average is about 337 watts per square meter. And also, the radiative forcing from carbon dioxide at, let's say, 100 years ago was around 32 watts per square meter, and now it's 33.7. So we're going up, the increase in the radiative forcing due to CO2 additions is about 1.7. Yeah, let's start. Now, nobody's ever talked about water vapor. Water vapor is a more potent greenhouse gas than carbon dioxide. It exists 25 times more than carbon dioxide, so the radiative forcing for water vapor has got 400 or 500. So when you add these together, they exceed the sun, so we don't need the sun to heat the earth. That's what I'm asking. I don't know if anybody understands what I'm saying, but this is seat of the pants engineering.
But how does the water vapor go into the atmosphere in the first place and turn into vapor form? How does it do it? It's all related to the energy that is deposited on the surface, even from land surfaces.
Right.
For ocean, obviously, this air, this solar radiation depends on the wavelengths. Actually, in terms of UV, ultraviolet, some of them obviously come in. They penetrate a little bit deeper than what you call the skin layer, you know? Not the microns effects. It's actually going down a meter even, okay? That's why the sun is such a grabber of the whole climate system, and then you created the water vapor, more evaporation. That's basically the whole idea, but the whole point is that you have to study it from the seasonal perspective. And then really, really study this thing in that sense that I'm talking about. So the water vapor, the short story is that water vapor effect is included. It's included. You can quantify the numbers, of course.
It's there? Where?
It's within the sun.
The sun?
Yep.
Because I was thinking of that sun is what's coming from, you know, the 200 or
Yeah, I'm just telling you that this whole
away.
thing is coupled. It's not so easy. If you want to start talking about that sense, I don't even like the idea of forcing put it that way. It's another convenient thing that doesn't tell you the truth. This is just a way in which that I'm trying to convey some of my message, why the season is so important. We will talk about it over beer, please.
Yeah, sure.
Thank you.
Yeah.
Which I'll be more profound, put it that way.
Sir, now the arguments over climate change or global change have sort of dropped off of the totally averaged effects, and the arguments are being made on the basis of regional changes and hurricanes and tornadoes and all that sort of stuff. Since you've worked a lot on regional effects of some of these things, have you thought some about the more current arguments about change?
Well, indeed, I tried to promote the idea. I was on the wrong path for a long time, global that. I always studied global temperature. Now I don't know what it means, and Professor Essex can tell you the problem in thermodynamics. But you realize that the whole system, how the energy got inputted, surely is the local regional phenomenon first. But the amazing thing about what the sun fingerprint is that it does that on a local scale, which you have to study, which is the example of the derivative of that, thanks to calculus, I guess. And then you also need to know the large-scale phenomena, how they are interrelated, which I'm trying to show with the equator to pole temperature gradient, which is the most significant dynamic variables in the climate system. You need both. I thought a lot about this. The bottom line is that, yeah, you really have to study on the regional scale, because I don't know what it means actually if you just take all this and without knowing the regional, local details. You'll miss all the point. And the system have memory and inertia. That's the whole thing. This is why you really need to know how does the seasonal response in the climate system works. No one knows actually. They claim they know, but it's not true. Howard?
As you know, the Vostok ice core data shows a correlation between CO2 and temperature for 100,000 years, but the fine structure shows that the CO2 changes after the temperature, leading to the argument that CO2 coming out of the oceans drives the that the temperature drives the CO2 which comes out of the oceans as it gets warmer. I've confronted IPCC people with this idea, and they say that is true. There's lots of CO2 in the oceans, 1,000 times as much as there is in the atmosphere, but there's no surface mixing between the surface and the deep water. You show that there is major surface mixing. Who's right and why? Now, is it true that it takes 100 to 1,000 years for CO2 from the lower part of the ocean to mix with the upper surface and go into the atmosphere?
Those are really a lot of details, which some of it I agree with you, but sorry for being a bit bored. I published the whole synthesis of this whole thing in 2007. I'd be happy to talk more with you and explain those things in details, but maybe we'll lose the audience. I already lost so many of you. Anyway.
I just want to thank you. Your correlations are very elegant, but the most important thing you say that ideologues don't say is, I was wrong. And
right. No, that's the whole thing. Believe me, I'm very self-critical.
Thank you very much.
Professor Cock-Hayden here would have some information for me on how to deal with this whole problem, but I have a lot more explanation to this. Thank you. I'll be around, so please talk to me anytime you want.
All right, we have a 15-minute break. We will start promptly again at 10:15, so please be seated at 10:15. Thank you.